Well, thanks for having me here. I'm excited to tell you about this activity that I made that focuses on the calculation that Katherine Johnson is perhaps most famous for doing for the U.S. space program. So I don't know if you've seen the movie Hidden Figures or not. But the situation in sort of 1961, 1962 is that the Russians had launched someone into space who came back again, but it was a bit like that Jeff Bezos launch, right? The Blue Origin, where they go up into space and they come back, they don't actually make an orbit. And so NASA was trying to catch up with that. And so they wanted to launch a person into orbit to make a couple of orbits and then come back again. So that person was going to be John Glenn. But the problem, as I'll explain in a second, is where to send the boats. Okay? So I don't know if you saw, did anybody see the Inspiration 4 launch mission it was the last 2 weeks? So they orbited the Earth a couple of times. I think they were up there for about 3 days. And then they came back, and then parachutes came out and they landed in the ocean. The thing that amazed me about this, besides the fact that it was the first all-civilian space mission, is that when they splashed down, you can see the parachutes here, here's the capsule, the boats were right there. Now, in 1961, this was not something that they were capable of doing. So in 2021, they were able to very precisely predict where that thing is going to land. But in 1962, this had never really been done before. And they were computers, they were relatively new on the scene, computers, that were predicting where the capsule would end up if they tried to do that. But John Glenn wasn't sure if those computers were right because they were very new, and he was skeptical, and his life was on the line because if they miscalculate where his capsule is going to land in the ocean, it could take hours and hours and hours for these boats to reach the capsule, get him out of the spacesuit, get him out of there. He's bobbing in 80, 90-degree heat. And so NASA wanted someone to double check the calculation, and so they assigned it to the best person they had, and that best person was Katherine Johnson. And so this activity is going to go into a little bit of what she calculated. So here's the link. So go.osu.edu/Project Mercury. If you want to open that up on your, you can watch me do it, or you can, if you want to do it later, you can open it up on your browser there. And so this kind of screen is going to come up, and then you just want to click this first link. And so there's a whole computer program here that I don't have time to kind of go over. On the YouTube channel, there's an activity called Slingshot with Gravity that goes into some of the stuff that's here. But you can go ahead and press play. I'm going to drag this over here and press play. Press play and see what it does. And so there's this little circle is supposed to be the Mercury capsule, and it's getting launched up this way. But what happens is it doesn't have quite enough velocity, doesn't have quite enough speed, and the gravity Earth sort of brings it back to Earth before it can make multiple orbits of the Earth. Now, the thing I love about this activity that I designed, and speaks to the power of play, is that you can touch the screen. You can touch, or you can, the mouse can touch the screen and click and drag, and you can sort of send this thing off, and just kind of explore the different kind of orbits that you will find. And so if the speed is only really slow, then you might start heading back to Earth prematurely. If it's too fast, you might head off into space. And you can do this anywhere. You can just click and drag and just learn through play about sort of how these orbits work. And it's all, fairly realistic. So there you go. There's the power of play. And so there's the power of play, but there's also computer science, there's also math, there's also physics going on. So that's what I love to do with STEM coding project. So all right. So 30 is too small of initial velocity, right? So the initial x velocity, the velocity horizontally is 0. It's 30 up. Let's make that a little bit larger. Let's try 35. And that goes a little bit further, but it's not quite enough. So let's increase that to 40. And now it goes kind of a quarter around, through a quarter of the Earth, I guess. Still not quite enough. So 40 is too small. Let's kick that up a notch to 50. See what that does. And yeah, there we go. So 50 can make a full orbit of the Earth. But there's a problem here, which is that, eventually we want to bring John Glenn back, and this is a little bit too far away, right? We don't need him to be this far away. So 50 is too much, right? So we tried 40. 40 was too little. 50 was too much. Let's cut the difference. 45. Okay, so 45, and yeah, that's basically the orbit that we were hoping to get. Okay, so according to this computer simulation, and by the way, computers are not to be trusted. Complex simulations are never correct because of their complexity, right? So, but according to the computer, initial speed of about 45 should give us what we need. So Katherine Johnson's job, remember, is to double check the result of the computer. So what we can do is we can use our physics and math skills to double check this result. So empirically, we find that with a velocity of 50, that's too big, too big of an orbit, and velocity of 35 is too small. So another way of saying that is that the radius of curvature here, and it's not a perfect circle, but the radius of curvature here is too big. The radius of curvature is larger than the Earth, whereas here the radius of curvature is actually smaller than the Earth, and so you end up coming back too soon. Now, it turns out, and so this is the kind of thing that Katherine Johnson would know about, that any object that's moving on any kind of curved trajectory is going to experience an acceleration that's related to the speed that it's moving and the radius of curvature of that curve. So it's a really sharp curve, then the radius is going to be small. The acceleration is going to be big, but if it's a nice gradual curve, then the acceleration is going to be small. And so this is true of anything moving in a curved trajectory. And we know that the acceleration is caused by gravity. That's right, we're going to double check the computer. So what do we know about gravity, and what do we know about forces? Well, gravity is a force. Force equals mass times acceleration. Gravity is gm m over r, and little m is the mass of the capsule, big M is the mass of the Earth. And then the distance from the capsule to the center of the Earth is roughly the radius of the Earth there. And that equals ma. Now, we can simplify this a little bit because this m is the same as that. So we can divide both sides by m and conclude that the acceleration is gm over r squared. And so that's the other thing we know. And so this is kind of what we've been seeing, that we have gm over r squared here. The radius of the Earth isn't changing much. The mass of the Earth isn't changing much, things like that. And so what we're finding is that if the velocity is too large, speed is too large, well then you end up with a large radius of curvature. But if the speed is too small, then the radius of curvature is also small. So what we really like to do is have the radius of curvature be equal to the radius of the Earth, which would look like this. And so now what we need to do is solve for v. All right, so put on your algebra caps, right? So we're going to solve for v. So what we can do is multiply both sides by r, right? And so this side's easy. R divided by r is 1, so those cancel out. And then this side isn't too bad, so r divided by r squared is r. And so we end up with something like this. And then now all I have to do is to figure out v is take the square root of both sides. And we end up with this, okay? So now the last step is figuring out what do we use for gm and r. Well, you could go to a physics textbook. And that would probably be the best way to do it, right? But an interesting thing is that this is a computer program, and for some strange reasons, I decided to set g equal to 100 and the mass of the Earth equal to 1,000, which is not correct. But the idea here is that I want to show how this capsule goes around the Earth, in a matter of seconds. I don't want to wait, 2 days or something as this thing goes around to animate it, and so you can sort of look at the parameters from the program and conclude that g is 100, m is 1,000, r is 50. And so let's go ahead and put that in and see what we get. So you can put that in your calculators, and it turns out that you get 44.721, which is remarkably close to what we found from the program of 45. So Katherine Johnson would say the computer's calculation looks okay. So I thought that was pretty cool. Now, obviously, this is not exactly the calculation that she did, so she had to figure out where this thing was going to land. So if you're curious about that calculation, there's a whole part two of this that's sort of like high school, maybe algebra 2, pre-calculus level. But it's there, and I'd love it for you to check it out. So there we go. There's your Hidden Figures STEM coding activity.